let's move on to the next part about pressure. So right now, I would like you to read about this. It's actually quite short in the textbook. Pause the video and come back to us. Okay, so first of all, you can see there's an equation here. This is also in the data booklet as well. So personally, I don't actually see we have to use this equation often. As you have learned in IGCSE, this is the equation for pressure when you applied a certain force onto an area with the surface area of A, and then you can calculate the pressure. And apparently, if area decrease, then pressure will increase, or if area maintain the same but then force increase, then pressure increase also. So it depends on the situation, of course. But then they also introduced in IB that the force may not be in the perpendicular direction to the surface. So you may have go in a certain angle, similar to what you may learn in other chapters. For example, in Chapter 5, you learn about circuits, and if you remember, the B field and current's direction may not be perpendicular to each other, so you may need to take the trigonometry, and therefore you may have the force to only be effective by multiplying with cosine theta, like this. So again, similar to Chapter 5 or some other cases like work done, etc. And anyway, I still don't see we have to use this equation a lot mathematically. So I would say you can keep this in mind, but I don't see it can get too complicated in the exam. Okay. As for the unit, is obviously you can deduce from the equation Newton per meter square for the pressure. You can also use Pascal if you want. And the main idea, I think the reason why they introduced this, because apparently in IGCSE physics, this is in mechanics, that chapter. So it would be very strange, actually, like the first time I see this in Chapter 3, I wonder why would they actually put it in Chapter 3, which is thermal physics. And I do think the only relationship or connection between this and Chapter 3 is later on you can use this to deduce further on the pressure in itself, because later on we'll talk about ideal gas law, and you think about those particles when they collide with the wall of the container, that collision is actually exerting a force onto the container. So we will talk about force over area as in the area of the container itself, and also force will be more like determined by the speed, because if you recall what force is actually changing momentum over time. So if you have a greater change of momentum, since the particle may be of a higher temperature, then it go faster to collide onto the wall. Say this is the wall with a certain initial velocity, and when they bounce back, maybe they have another velocity, and therefore if you have a greater temperature, hence a greater speed, then you have a greater change in momentum and greater force, and that would be a greater pressure. Okay, and that is basically one of the questions here. Then you can put down the answer on how to deduce how the average speed of the molecules affect the pressure in a container. Using this is one of the idea, which is a formula you have to follow. Okay, so the last thing that we will include in this video is one example here. So you may want to read the question. I don't think I have included that into the question booklet, but you can read it, and I think we will go through the answers directly on the textbook. So you may want to pause the video first. Okay, so this one is, since simply is too simple, so I will just go through it with you. So first of all, it said there's a hollow tube with the side of this, so some dimension we can help you calculate the area. One face missing are placed together at the missing face, and the air are pumped out, so no air inside. Determine the force necessary to separate the cubes. So this one is a very interesting or classic physics question, because if you have seen those kind of air seal hook, let me show a picture, which is more like this kind of hook, and the mechanism probably you know is making the surface between the hook and the surface vacuum, and so the air pressure basically help you to hold this into place. If you know about this guy, Professor Tong, he also did an experiment long ago. He tried to hang a person using this kind of hook, and the calculation was actually quite interesting. So it could actually predict quite well using the law here. So here's a similar idea, and so simply what you could calculate is using simply the equation itself. So the air pressure would simply be the atmospheric pressure in itself, because again inside it is 0, so the change in pressure is simply the atmospheric pressure itself. So by substituting, you should be able to find the answer if you remember to use the SI unit.